regression. Okay, so the input to a regression problem, or sometimes called as the training data, is just a bunch of x1 to xn, where all xi's are in d dimension, and y1 corresponding y1 to yn, where yi's are in reals. This is our input. Now, what is the goal of a regression problem? Well, the goal of a regression problem is to learn how to predict for a given new feature, which means that we basically want to learn a function h which maps Rd to R. Well, Rd is our feature space, right? So, all our features are in d-dimensional vectors. That is what we are going to think of them as. R is our label space, and we want a function that maps given a feature to a label, a good function, right? So, so of course, given the data, we want to learn a function h which can then be used to predict for future, input instances. The question is, there are so many functions that map Rd to R, how do you learn a good function, right? So, the question is, how do we measure goodness of a function? For instance, if I give you a function from Rd to R, and then I ask you how good is this function for this particular data set, because at the end of the day, the goodness has to somehow depend on the data set. So, you have the data set at your hand, you do not have the function, but if I give you a function, can we say how good is this function to this data set? If we can do that, then perhaps we can then search for that function which is the most good, right? So, it is in fact the best function for this data set somehow, right? So, which means that we need to come up with some notion of error for a given function, right? So, error of an h. I give you an h, and then you have to output a number, a single number, which tells me how good is this h for this data set. So, what might be a good way to measure error? Well, let us take a single data point xi, ith data point in my data set, and then ask how good is h for xi. The label for xi is yi, but then h makes a prediction h of xi. Now, we have two numbers, h of xi and yi. We somehow have to compare them, right? So, one natural way to compare them could be by looking at h of xi minus yi the whole squared, right? So, this is the squared error between what my prediction is and what the actual value is, right? So, this is not necessarily the only error that you can think about. Maybe you have a different error in mind. I mean, anything that is reasonable is okay, but then we will start with squared error. We will see, we will justify squared error in different ways later on, but for now it seems like, you want the error to be non-negative first of all, because if I, for instance, if I just take h of xi minus yi as my error and not use the square, then I can always output a function h which sets for every xi the value of minus infinity. It outputs minus infinity such that my error is as small as possible, right? So, and that's not really learning anything. That's like a I mean, that function is useless pretty much for prediction. So, we don't want such useless functions. So, we choose our error a little bit more carefully. In this case, we set it as squared error. We will justify squared error in much more detail later on. Okay, so now this is for one data point, but then we have n data points. So, what you could look at is just the summation of phi equals 1 to n over all data points. Okay, so this seems like a reasonable place to start to look at how to model, how to measure error of a given h, right. So, if I give you a h, now you know how to find the error of this h with respect to the data set, which is good. So, now what is our goal? Well, our goal is to find that h that has as small an error as possible with respect to the data set, right. So, once a measure of goodness we have put down, then the goal is to find an h which has as small an error as possible. Now, here is a question for all of you, right. So, how small can this error be, right? So how small can this error be, right? So in the best case, right? Pause and think about it. I'll tell you the answer. This error can be as small as 0, because it's a sum of squares, and squares are non-negative values. So you are adding a bunch of non-negative numbers. So the smallest value that it can take is 0. Now when does it achieve 0, right? So which h achieves 0? Which h achieves 0 error? Now what is the property of the h that achieves 0 error, right? So if you stare at this error function that we have put down for a while, you will realize that, well, the h that achieves 0 error is the one that satisfies h of xi equals yi for all I. Only then our prediction and the actual values match, and we will have 0 error, right? Well, the question is, now we have come up with a error function which we want to minimize, and then we are saying that, well, we can minimize this, right? So we can always find a h such that if you give xi, I will just output yi, right? So which means that with respect to the training set, I exactly match my labels of my training set, right? So my error in the training set is 0, which means if you really wanted to minimize the training error, then you have already done it, right? So h that does this is given to you. Now the question is this a good h? Are we happy with this h with respect to the linear, with respect to the problem that we care about here, which is the regression problem? Well, there are some reasons why you may not necessarily be happy with this h. I would want you to think about this, and then I'll give you some reasons why. What is the problem with this h, right? So what is the issue? What is the problem here? Well, what has happened is that the h that you have come up with, you can think of this h as somehow having memorized the mapping from xi to yi, right? So for every xi in the training data, my h will give you the exact value for yi. But is memorization really what we want to do? We perhaps are very good with respect to the training set, with respect to our exercise problems, but then in the test, well, have we really learnt by memorizing, right? So that's the question we are trying to ask. In other words, we are asking somehow, are we overfitting to the training data that we might not do well perhaps on the test data? Now what does it even mean to say we are overfitting? It's not clear at this point, but then it looks like, if you just do well on the training data, it may not necessarily translate to good performance on the test data. So we'll first try to see where this leads us to. Basically, we are saying by memorizing, we notice that we can get 0 error on training data. But our goal is never to do well on the training data, right? So a spam classifier, or in this case a rainfall predictor, may do perfectly well for predicting the rainfall for the previous 3 years. But then if it's a useless predictor if it does not do well on today and later on from tomorrow, right? So because the whole point is to do well on test data. But by memorizing we can do well on the training data. Now what we care is about the test performance. Now the question is, what are we missing? Now there are a lot of things which could have gone wrong in our line of thought here. One choice that we made is the error function, which is the squared error. Now we can either suspect that to be a problem, or if that is not a problem, then where else is the problem? Why are we ending up memorizing this? If you think about it, the problem is not really the fact that we are choosing a squared error. The problem is that we are allowing for all possible functions to be our search space. If we allow for h to be from any mapping from RD to R, then naturally you will end up finding that h which ends up memorizing, and hence perhaps will overfit. So what do we want? How can we remedy this? We can remedy this by restricting the space in which we are searching for h. But then what does that mean? That means that you are searching for certain structured functions that map RD to R, which means that we are assuming that the real mapping from RD to R has certain structure, which means that we make that assumption that we impose a structure on the true mapping between RD to R, and then we can assume that, well, now I am only going to search in a smaller search space, I am not going to allow all possible H's to be possible, maps from RD to R. Let me make it a little bit more clear now. Basically, our goal now is to somehow say that we will still live with the squared error, but then we will impose some structure. Let me use a different color to highlight this. We will impose a structure to reduce our search space. Now, what is the simplest structure that you can think of that maps RD to R? Well, one simplest structure that we could impose is the linear structure. In other words, what are we saying? Well, we were initially searching for in this bigger space of functions, which is the set of all functions H from RD to R. Now we are saying, well, we don't care about the whole set of functions, we are only going to look at a smaller set of functions. This is the set we are going to call as H linear, which is the set of functions which are, let us call H from RD to R, but then this H is, I am going to think of this as parameterized by some W, such that it is a linear function of the input, right. So, a simplest linear function could be of the form HW of x, given an x, well, this is parameterized by W and it is a linear function. So, this will look like something like W transpose x, right. So, for all W in RD. Of course, one can use in one dimension, this is like saying y equals mx, right. So, but you might ask, where is y equal to mx plus c, which is also a line, it is a linear structure. We can work with that also, we can impose that structure also and call this W transpose x plus b. But for simplicity of explanation, I am just going to use just W transpose x as the simplest linear structure. Whatever we talk can be adapted to the case where we have W transpose x plus b for some shift of these lines also. That it is kind of straightforward to do that. We will see that later. Okay. So, now what does it mean, right? So, now what does it mean to say that we are imposing the structure? Now, what are we making an assumption about the data? Well, the data's real relation between the features and the labels is a linear relation, but there might be some noise in the output which might not make it look exactly linear. But then still, because we are imposing or we are hypothesizing that there is a linear structure between input and output, just everything else is noise, we do not want to search in the space of entire functions, because that will also end up fitting the noise, which is what we are going to think of as overfitting, whereas we will only fit the structure, which means we will only search in the space of linear functions, right. So, now what is our modified goal then? Our modified goal is the following. So, we are going to minimize over HW, every HW in H linear, we are going to search in this space the same error function. There is no problem with the error function, right. So, HW of xi minus yi squared, but we know how HWs look like, right. So, or equivalently, the problem that we really want to solve is, well, because HW is parameterized by W, we can search for W in RD, sum over I equals 1 to n. HW of xi is just W transpose xi minus yi squared. Now, this is a regression problem, but because we have imposed a condition that we are searching in a linear space of linear functions, this problem is called as a linear regression problem. It is simply saying that you have a bunch of features, and then the best way to explain the label given the features is by doing some weighted combination of these features. The weights will tell you how important each feature is, and then if you do a weighted combination via W transpose Xi, then that will give you essentially a good fit for the labels. Now, if you think about it, now one can ask how small can this function, this new objective become. The question that we asked previously, which led us to understanding of overfitting, but now we can still ask the question, how small can this become? Well, if you think about it, this can also become 0, right? So there is nothing, I mean, it's still a sum of bunch of squared non-negative numbers, it can still be 0. But now, will we call this overfitting if this becomes 0? No. Why? Because when will this become 0? This will become 0 when W transpose Xi equals Yi for every I. That means that our labels exactly correspond to the structure that we have hypothesized as the essential structure that maps input to output, which means there is no noise, right? So, which means we have exactly fit a structure and then the labels correspond to that. So, that is not overfitting, right? So, that is the fit, that the best fit in the structural relation that we have imposed actually ends up being so good that we are getting a 0 error. That is what that would mean, right? Whereas it would mean overfitting if we search in a bigger space of functions than the actual relation that maps the input to output, right? So, that is when you will start fitting the noise and then overfitting happens. We will talk about this noise more probabilistically later on, but for now it suffices to think of them as just some additional value other than what the structure is giving you, which is nonsensical, right? So, for with respect to prediction.